Yes, sir.
Let's have a system of you guys responding every few minutes. So if something goes wrong, I know. So I'm going to quickly show you the blackboard from yesterday. Yeah, somebody is speaking the background. Who is that? Okay, all right. So yesterday we began with revising something about sets. And we said every object that we'll consider is a set. But today we'll consider some non-set objects. But all right, most of the objects will be sets. Sets are not defined. But of course, we have something in mind, and that is a collection of some sort, but collection without any further structure. So it's like a handful of sand. All the sand grains are not connected to each other in any definite structure. Now, the collection is of other sets, and those sets are in turn collections of other sets. And this goes on and on till you need a starting point, and that's the empty set. So this is the empty set. And between two sets, there are two kinds of relations possible. One is equality. Equality means they are one and the same. And the other is membership or belonging to. And you know both these relations practically for the last 15 years, I'm sure. So as an example of how sets are built out of empty set alone, I gave you example of natural numbers and told you how one can model 0 as the empty set and 1 as the set whose only member is 0 and 2 as the set whose only members are 0 and 1 and so on. N is the set whose members are 0, 1, then minus 1. So notice that this modeling achieves the correct size so that the set that we have defined to be equal to n has cardinality n. So if something is in bijection with this set, then that other thing has size n. Something is in bijection with this set, then it has exactly two members. And that is the purpose of natural numbers, to be able to count, and this does the job. And I told you that if you want to know more about sets, you can look at Helmholtz's naive set theory, a very nice book. Naive means non-formal language style, but addressed to mathematicians. Now, one of the important jobs that we had to do with sets, after saying that everything is a set, is to explain then what is an ordered pair. Can an ordered pair be explained as a set? And then we gave one modeling of ordered pair, and it achieved this property, which was exercise 40. Then I told you about Search-Lang's algebra, which is a somewhat more modern book in our textbooks, usual textbooks, and uses things like categories, etc. in modern sense. However, the definition of a functions is still not very satisfactory in all these standard textbooks, because a function has to have three things. One is a domain, one is a codomain, and one is information about what is being sent to what. That what is being sent to what is represented by the graph, which is a subset of x cross y. So therefore, a function for us is a triple, x, y, and the graph. And the graph is a subset such that for every small x, which is a member of this x, there exists a unique small y in y such that this x comma y is in the graph. Now, I told you that this product comes with such a map and another such map. And at the level of elements, you know what it does. It sends the pair small x comma small y to x or y. Now this has a wonderful property, call its universal property. Namely, if there is any other set with one map to x and one map to y, then there exists a unique map to x cross y making the entire diagram commute. And that map has to be defined by this property. So it doesn't matter how we constructed x cross phi. We constructed it as ordered pairs, and the ordered pairs we constructed by this recipe. It doesn't matter. What matters is this property. So somebody else might have made this product P as column matrices X and Y and defined the projection as the top element and the bottom element. But it will have the same property. Therefore, between your construction and his construction, there will exist a unique bijection which makes all the diagrams commute. That is what makes this product. Product is such a triple, a set, first projection, second projection. Unique up to unique isomorphism. Here isomorphism is in the sense of sets, which means a bijection, which actually means a map which is invertible, for which there is an opposite map such that both composites are identities. Identity map is a map whose domain is the same as its codomain, and the graph is the diagonal, small x comma small x. So then I defined for you a singleton set. A singleton set is a set which is not the empty set, and if there are any two members, then they are equal, which means one and the same. So and I showed you some examples of singleton sets. A singleton set is unique up to unique isomorphism. But a set of cardinality too, there are many of them, and there are multiple isomorphisms within them, or there are multiple automorphisms of each, because you can have identity or you can have the permutation. A set of cardinality n has factorial n automorphisms as sets. And I reminded you something you know from your field theory, that if real numbers have two different algebraic closures, then between those two closures, there will actually exist two different isomorphisms which are identity on R. So each is C, and you know how it looks on C. Z goes to Z and Z goes to Z bar. This is quite unlike the situation of completion of a metric space, where if I have metric space, I have its completion, and I have some metric preserving map to some other complete metric space, then there exists a unique metric preserving map from this completion to that. The completion behaves quite different from algebraic closure. I also showed you here another model of natural numbers, and I told you that natural numbers are unique up to unique isomorphism, not just the set, but set equipped with, say, the total order. If it's only a set, then what's so special about 0 and phi? All interchangeable. If it's only a set, it has a huge permutation pool. But no, there's an order on it which has to be clear. Then I told you what's a family. A family of sets indexed by a set I. And then I told you what is product for a family. Then the indexing set consists of just two members, then that's your binary product x cross phi. Binary means two, bicycle, binary. Bi means two in this context. So binary product you always know, and this is product over a family, which generalizes that. And I gave you a construction for that and told you its universal property, that it has all these projections, and this tuple, this P together with this Pi, is unique up to unique isomorphism. If there's any other W with maps Fi to the Xi, then there will exist a unique H from W to P. How do you define H? Well, send any small w to the family FIW. Then I gave you this exercise that suppose the indexing family was empty, then what is the product? Okay. At this point, I want to hear from you. Are you with me so far? You guys have heard this much?
Yes, yes.
Very good. Now let me come to disjoint union. So this is in some sense opposite of binary product. This is binary coproduct. So product, coproduct, the kind of dual of that. Homology, cohomology, and so on. So which in sets is achieved via disjoint union. How to make disjoint union? You need two copies of something, and to produce two copies, I just converted everything into ordered pairs and added the second element to be 1 or second element to be 2. Now it is disjoint because in this copy everything looks like small x comma 1. In this copy everything looks like small x comma 2. And they can never be equal because this can never be equal to this. So now they are empty, and now you can simply take union, and that's the disjoint union. Now this is a construction. Instead of taking 1 and 2, I could have taken here any set, and here I could have taken any set, and I could have formed a singleton set whose member is anything of my choice. So there can be many different constructions. Or I could have changed the order. I could have taken this fellow on this side and this on that side. But whatever I do, actually it's a property I'm looking for, and the property is this. X has a map into this disjoint union, Y also has a map into this disjoint union, with the property that if both X and Y have some maps into some other set W, then there exists a unique map from this disjoint union to W, making this triangle as well as this triangle commutative. And that makes this triple X disjoint union Y, Jx and Jy. This triple becomes unique up to unique bisection. This becomes unique up to unique isomorphism. Okay. So this is what is described there, and then I asked you to describe disjoint unions. Well, okay, I told you what's a disjoint union indexed by an arbitrary family. After binary disjoint union, I took disjoint union of coproduct or arbitrary family, indexing family I, family indexed by I. And then I asked you that if the indexing family is empty, how does the coproduct look? And the last item was I introduced to you the word initial object and final object. Here our objects are sets. So initial set, final set. So X is an initial set. What's the definition? If given any set Y, there exists a unique map from X to Y. And it's a final set if it's the other way around. And I asked you to tell me what were initial sets and final sets, which I think one of you did on the spot, but others would need to think about the answer even if they hear about it. And by now, I'm sure everybody has figured out the answer. And so this initial set is the empty set. And the final set is any singleton set. So are initial sets and final sets unique? Well, initial set is physically unique and it has no automorphisms except identity. And final set, you can have your favorite initial set, but again, the only automorphism is identity. Only automorphism being identity is important here. Physically, how you do it doesn't matter. Okay. All right. So this last thing looks like I was answering some nice questions you guys are asking. Okay. So that is the review of my last lecture. So now any questions about yesterday? Okay, are you guys with me? Should I begin on today's material? Bolo, awaz.
Yes.
Good. So let's start. All right. So there should be some. I should type something. Okay, the kind of things I want to discuss in lecture 2 are categories. So we won't define categories. Okay, I think I need to change the color of this. Looks too bad. Okay. So let's give some examples of categories. So can categories be defined? Well, you need to do a lot more work if you want to define categories. So it's, on the other hand, the categories that we will need are only a few, and so we will I'll define them by giving you examples. So one example that we will talk about is sets. So it has some objects. It has some arrows. And the arrows have composition. And there is identity. And there is associativity of composition. This composition is associative. Okay? And this identity arrow for each object. Close an identity arrow for each object. So let us see, we will see, I'll put a kind of colorful, well, all kinds of things are possible in this, that's wonderful. Okay. So I'll put this big box around here, okay? Objects, arrows, composition, with associativity, composition has associativity, and each object has an identity arrow. So let's see what are the objects. So the objects are sets. Each set is an object of the category of sets. So here I'll say the category of sets. Category of sets. Objects are sets. Individual sets are objects. Arrows, X, Y, etc. These are objects. Arrows are maps. And each arrow has a domain or source, and a codomain, also called source, also called target. So what is the domain of this map? X. What is the codomain of this arrow? Y. So arrows are maps. Domains are the domains of maps. Codomains are the codomains of maps. Or this X is the source of this arrow and Y is the target of this arrow, because the arrow is going from X to Y. Now there is composition. If there is another arrow from Y to Z, then I get a composite arrow, which I write as G composite F. And then you know associativity means there is X to Y to Z to W. I may first compose this and then compose this with this, or I may first compose this with the composition of this with this. And I'll give these names F, G, H. And associativity means H composed with G composed with F is equal to H composite G composite F. So that is composition and its associativity. Now I need an identity arrow for each object. Yes. So here is an object. Object is a set, and I need an identity arrow for each one. That's the identity map from X to X. Okay. So how does the graph of identity look? Graph of identity, this is X, this is X, this is X cross X, and this is the graph of identity X. Because any element here is small x comma small x. That's the identity. Yeah. So let me ask you guys. So have you understood the category of sets as far as these words are concerned? Yeah, any doubt? See, these are very, very important concepts. So you make sure you understand it clearly. Okay, now I said I'll introduce categories by example. So let me come to a new example in a new color. My next example is the category of groups. Objects, groups. So you know what's a group. A group itself is a pair like this, where this is a set, non-empty of course, and this is a map going from G cross G to G, which is the multiplication map, and etc. etc. Associative, identity. So this is mu. Mu is associative, identity element, E, and inverse. So everybody knows what are these objects. So these are the objects of the category of groups. Now somebody tell me what arrow should I take in my category of groups. So by the way, this pair, you are pretty used to this abuse of notation, that this group is not usually written as G comma dot. It's simply written as G, and we suppress the notation for dot. Yeah, the notation for dot is understood. This is simply denoted by G. With dot as understood. So now what are the arrows? So if I have group G, yeah, tell me.
Yeah, the group homomorphisms.
The group homomorphism, exactly. So there are various arrows from here to here. Okay. So these are the group homomorphisms. So there is a certain notation. The notation is arrows from G to H. Or sometimes it is written as morphisms from G to H. Either of the notation used, this is a set. So with this as the arrows, let us check whether the other things in the category are satisfied. So does every arrow have a source domain? Yes. It's from G to H. G is the domain and H is the codomain. Can you compose group homomorphisms? Well, these are maps. We can compose them as maps. The only point is the composite again a group homomorphism? Yes, it is. No problem. Is the composition associative? Yes. Being composition of set theoretic maps, it is associative. Is there an identity homomorphism? Yes. Send every group element to itself. That's also a group homomorphism. Okay. And it's both left and right identity under composition. What is the property of this? What is so great about this identity? Namely, if I take G to G, identity G, and if I take G to H, some other phi, then phi composite identity G is equal to phi. This means this identity has this property, great property of being or if I take some k to G, some psi, and G to G identity of G, then I have identity G composite psi is equal to psi, which means this identity acts like left identity as well as right identity under composition. So let's go back there. Yeah, there is an identity arrow for each object, which acts as identity for composition. this I had not written here, which is left as well as right identity for composition. Okay. So we have the category of groups. Now I am going to introduce one more category in one more color. So here's my new color and here's my new category. My category of real vector spaces. Okay. Objects. So what should be the objects? Vector spaces over R. V vector space over real numbers. Arrows.
Linear
What arrow
transformation.
should I take from V to W?
Linear transformations.
Linear map, correct. Linear map. F, which means F of U plus V equal to FU plus FV, and the second thing is F of some lambda times U has to be lambda times FU. Notation is obvious. Lambda belongs to R and UV belongs to V. Okay. So those are the arrows. Now I leave it to you to supply the remaining data. How do I compose arrows? Well, you compose the linear transformation. That composition is of course associative. There is an identity linear transformation. In matrix terms, in case your vector space is finite dimensional, both vector spaces are finite dimensional, then the arrows can be printed through matrices, and then composition is by multiplication by matrices. Once you choose basis, an identity arrow will become the identity matrix. And it's both left and right identity for composition. Thus, square identity matrix is both left and right identity for matrix multiplication. Same properties. Okay. Now I can go on and on and on, but now we will introduce two very important categories. Well, actually a number of categories whose objects are matrix spaces, but arrows are defined differently. And there will be another category called the category of topological spaces. And most of our course is the study of this category of topological spaces. Okay. Now it's very important to go back and forth between categories. One can use one category to help you in the study of other category. So the category of, say, commutative rings or abelian groups or whatnot can be used to help you study topology, and then that subject is called algebraic topology. You are taking the help of an algebraic category in order to solve problems in the topological category. And this translation of problems is done via something called functors, which go between categories. So they translate problem in one category into another where it may be easier to solve. So different subjects apparently may compartmentalized actually are related by these functors which go between various categories. Yeah. Okay. So having introduced all this, now I am going to again get back to general theory with these examples. I said I am going to introduce category via examples. So I have said what's a category, and I have given you 3 examples. And remember, I have not defined what is a category. I only told you its general properties, and I have given you 3 examples where you could see that those properties are satisfied. Okay. So now let me introduce one more general concept called final object in a category C. Okay, which means such a final object, let's call this final object F. F. This should have the property, definition is any object X should have a unique arrow to F. Okay, so there should exist there should exist a unique such arrow from X to F. Okay, let's call this arrow P. Now I am going to ask you category by category what are the final objects. So I'll name the category, you tell me what is, and I'm changing the color because we are now talking examples. Okay. So category of sets, what's the final object?
The same set.
Any singleton set.
Oh, okay.
F can be any singleton set. Groups.
The trivial group.
That's one point group.
Yeah.
Trivial group as you called it. Final object, a singleton group. What was the other thing we introduced? Real vector spaces, R vector spaces. Here the final object is the vector space 0, 0 vector space. Any other vector space has a unique map to the 0 vector space. Let me introduce one more category, commutative rings. Now, I have not introduced this example, but let's go back one by one. If I say category of commutative rings, you are supposed to answer loudly. What are the objects?
Commutative rings.
What are the arrows?
Ring homomorphism.
Ring homomorphisms. And remember, a ring homomorphism is supposed to take 1 to 1.
The identity
A
of
ring
the
homomorphism has a domain and a codomain, and you can compose them, and composition is associated. What is the identity arrow of a ring? The identity homomorphism from ring to itself, sending each element to itself. Okay, so it's a category, all right. So what is the final object in the category of what is the final object in commutative rings? Bolo.
Set containing 0 and 1.
No.
Are you allowing 0 equal to 1?
Yes, I have to allow it.
Yeah. Then
So the 0 ring, which means 0 is equal to 1. Then given any other ring, it has a unique homomorphism to this ring. Okay. Think over, you have to mull over these examples, get the hang of it. Now I'm going to introduce the concept of initial object, which is the opposite concept. Initial object A in a category C. Okay. What's the definition? Given any object X in C, there exists a unique arrow. Let's call it UX, going from A into X. See what has happened ulta, X to F, instead here A to X. I have reversed the arrow. Okay. So now we are going to run through examples again. So tell me, one by one. For sets, category of sets.
It's empty, the empty set.
Correct. Initial object, empty set, because given any other set, there's a unique map from empty set to it. Next was what category? Groups. So see here, the initial object is not the same as the terminal or final object. The final object was a singleton set, and initial object is the empty set. So in sets, these are different. Next is my category of groups. Here the initial object is
Trivial.
The trivial group is the initial object, and which was also the terminal object. Final object is also called terminal object, by the way. Final or terminal. It's like the railway ends there. It's railway terminal. Okay. So final is this. Next was what category? Real vector spaces. Okay.
Again,
Vector
just 0.
spaces over R, yeah.
Just 0.
Again, it's the zero vector space. And the last one was commutative rings.
Z.
Wonderful. So whosoever gave this answer gave the correct answer, and now just justify this answer. So given any other ring R, there's a unique homomorphism from Z to R. You know why? Because 1
Yes, you.
has to go to 1. And if 1 goes to 1, then 1 plus 1 has to go to 1 plus 1, and minus of 1 has to go to minus of 1, and 0 anyway has to go to 0. So everything is determined. You have absolutely no choice. So there's a unique such arrow. So again, the initial ring is not the same as the final ring. Final ring was 0 and initial ring is Z. Yeah, so these different categories behave a bit differently, though the arrow theoretic properties are very similar. So any questions at this point? You understood the notions of a category, an initial object, and a final object. Therefore, time to introduce more words. Now I'm going to define binary product in a category C. Okay, so X and Y are two objects. It could be the same object taken twice. And then a binary product is a triple. What we are looking for is a triple. The triple is X cross Y, P, X, and Py. Such a triple. That's a binary product. And what is X cross Y? This is an object. This is an arrow from X cross Y to X. And this is an arrow from X cross Y to Y. And it should have universal property. The property is this, that I have this X cross Y with this P, X, and Y. So Px, Py, whatever. Now suppose I have any other object W and any two arrows. Then there has to exist a unique such arrow H. So given any F and G like this, there has to exist a unique, so that this triangle commutes and this triangle commutes, which means this composite, which is defined in any category, is this, and this composite is this. You understood what's binary product? So binary product is unique up to unique isomorphism. So if I have one product X cross Y, Px, Py, and another candidate for product P, Q1, Q2, then there will exist a unique isomorphism. So I should introduce the word isomorphism. There exists a unique isomorphism H such that what?
Such that everything commutes.
So what are these everythings? So here
Yeah.
is E, here is H, and here is the projection to X. Here is the projection to X. This is P, this is Q. This has to commute. This is Px, Q1. And similarly the other one, X cross Y to PH. This is Py, this is Y, and this is Q. All these commute. So this brings me suddenly to the realization that I never defined for you what's an isomorphism. So
Yeah,
an
so
arrow x to y in a category in C, given this arrow. And suppose there's another arrow, G. Suppose there exists such that GOF is identity of X and FOG is equal to identity of Y. Okay? Then we say that F is an isomorphism and G is its inverse. Okay, check if there are two inverses. If an inverse exists, it is unique. Also check this G is an isomorphism with inverse F. So you write it that F inverse is G and G inverse is F. So pretty familiar, yeah? It is familiar to you in all these examples. In each one of these examples, you have separately studied this. And now we are putting it in an abstract, very simple formulation called category theory. So the notion of an isomorphism is something which is categorical. Okay? Yeah. So you have checked laboriously once that if a matrix has a left inverse and square matrix and it has a right inverse, then the left and right inverses are equal to each other and so on, so on, so on. And by doing matrix multiplication formula, and you have checked it in your group theory that if an element in a group has X as its left inverse and Y as its right inverse, and X equal to Y. And you have checked it in all such examples. But it is actually completely abstractly true, and it is abstractly true by simply following just these rules of a category. Just from this much you can argue and get all of that. So you don't have to separately argue in different categories. You can forget what is the substance of that category as far as categorical arguments are concerned, which are just using this. Do you know the meaning of the English word abstract? Abstract is to take away, to steal, okay? To take something out. So abstraction means you have taken out all the irrelevant, useless detail and just retained the core things. That is abstract. So category theory is an abstract presentation of many of the common arguments you have always made. Okay. So at this point, I have told you what's a category and what are isomorphisms, what are binary products, what's initial object, what's terminal object, and I am going to tell you what's coproduct. Binary coproduct. So this is still theoretical stuff. So let's introduce coproduct in a category C. So X, Y are objects. And this binary coproduct is a triple again. There is yet another object. This is an object. And then there's an arrow J1 going from X into this. And there is J2 going from Y into X. Such that what? Such that the following universal property holds. So universal properties, I have this from X into X disjoint Y and Y into X disjoint Y. This is J1, J2. Now suppose there was any other object Z and two arrows F and G, then there exists a unique such arrow H which makes this triangle commute and this triangle commute. And I'm not going to write it all in words. Okay, pictures are better than words here. And so once again, if there's another candidate for the binary coproduct, there is a unique isomorphism between your candidate and that other candidate, which makes the first map go to the first map and second map go to the second map. Yeah. So now we'll look at examples, and I leave it to you to define, instead of binary product, a product over a family of objects, and a coproduct over a family of objects in any category, mimicking the universal properties that you see here. I'm not going to write that. I'm simply going to write just the names. Product of a family of objects in C parameterized by a set I. Similarly, coproduct. So this product is written like this: I belonging to I, Xi, and the maps are called Ti. Maps are arrows. And similarly, coproduct. And that is the coproduct sign, I belonging to I, Xi. And this Pi, instead of Pi, I'll have whatever I called it, Ji. Ji is going in the opposite direction, from Xi into the coproduct. And this Pi is going from the product to Xi. So I am leaving the definition to you because I am in a hurry to get back to my examples. And now, as we have only 10 minutes left, so I want you to tell me what are the binary products and the binary coproducts in all this category. So let's take the category. Okay, now it's examples. So here I say binary product. Or you can write it as alternative notation is X cross Y, and the binary coproduct. Okay, so let's start with sets. So what is this? This is the Cartesian product X cross Y. And with the projection so you see, we have suppressed the notation PIs and we have suppressed the notation JIs. Okay, and here it is X cross 1 union X cross 2 and so on, and with X mapping inside here and Y mapping inside Y cross 2. It's not X. Now now comes fun. So now I have groups. So I have two groups G and H. Can you tell me what is the binary product of two groups?
The product.
The product group. Okay, product group, direct product of groups. It's called direct product. Its elements are of the form G comma H. And the multiplication is G comma H times G prime comma H prime is equal to what? Tell me.
G prime comma H prime,
etc. etc. And the projections are send this to G, send to that. Those are group homomorphisms. Now, what is the coproduct? There's a traditional notation for the coproduct, and the coproduct is denoted something like this.
Direct sum.
product.
Huh? What?
Yeah, the direct sum or
Direct sum? No, it's not.
Oh, that's for abelian. This is the free product.
Maybe. This is called free product.
oh,
This is called free product.
mm,
If you have not seen the free product, go see it in your algebra textbook. It's called free product. And you see, you simply start taking products of elements G1, G2, H, then some more G prime, blah, blah, G double prime. Then you take some other element H1, H2. Just keep this product. Now evaluate this product using the rule of G. Evaluate this product using the rule of H, so that now you will have elements of G separated by elements of H and no further contraction possible. Yeah. And now when you multiply two things, if two G things come together, carry out the multiplication in G. If two H things come together, carry out the multiplication in H. How do you write the inverse? Write everything in reverse order and put an inverse on each element. And that will be the inverse. Yeah, you get the idea how to make free product? I quickly told you. Okay. So already this is territory which some of you don't know. Now, to give you a very nice example, what is the free product of Z, free product with Z? This is called free group on two generators. All right. While here Z product with Z will be Z direct sum Z. Here it will be Z direct sum Z. This is commutative. This is not commutative. Not abelian. So even if you begin with two abelian groups, their free product may not be abelian. The direct product will remain abelian. Okay, let's go to the next category. What was our next category? Vector spaces. Okay, wonderful. Vector spaces, the answers are easy. What is V cross W? Or it's also written as V direct sum W. And this is also V direct sum W. You know, the product and the coproduct in binary product equal to binary coproduct. This is very funny for vector spaces. Binary product in vector spaces is the same as binary coproduct, except the projections are different. This is the underlying vector space. Underlying vector space.
Hello, sir.
Yeah.
So these vector spaces are finite dimensional, no?
No, they need not be.
Okay.
Okay. Now, but something funny happens for infinite products. Product and infinite coproduct. These are very different. Even the underlying vector spaces are different. Underlying vector space. See, for example, if each of my vector spaces is R and my indexing set is natural numbers. So suppose indexing set is natural numbers and each VI is R, suppose. Then the product of VI is this infinite product. And the coproduct of VI is this infinite sum. These are all tuples. These are all tuples. X0, X1, X2, blah, 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 blah. And these are all tuples. X0, X1, X2, blah, blah, blah. 0, 0, 0, 0. So only finitely many entries are 0, non-zero. finitely many non-zero entries. And all other entries will be zero. In product, you can have all entries arbitrary. And you check that this is an exercise to you in linear algebra now, that this behaves like product. And what is the projection? Projection sends this to xi. This is the projection pi. And the map J from R sends xi to 0, 0, 0, x 0, 0, 0. This in the ith place. Okay. So you understood what is the binary product and binary coproduct, as well as arbitrary family product and arbitrary family coproduct in vector spaces. What was the next category?
The commutative rings.
Commutative rings. Great. So let's stick to binary there. Otherwise, it will become a course in commutative algebraics, right? So suppose I have rings, commutative rings. So I have two rings, A and B. And here's binary product. And here is coproduct. So the binary product is this direct product of rings together with projections. So what is the element of the binary product? It is A comma B. How do I add two things component wise? How do I multiply them component wise? Yeah. So A plus A prime comma B prime is equal to A plus A prime B plus B prime. Same for multiplication, etc. And coproduct, somebody tell me, and we have exactly 1 minute left. Chalo, tell me what's the coproduct.
The
yeah.
tensor. The
Tensor product. What's your name?
Himanshu.
Acha, Himanshu, you are right, and that's a good answer. And this is called the tensor product over Z. Except I'm not sure that everybody in this batch has understood your answer. Therefore, I won't pursue it. But soon you are going to learn tensor products in your commutative algebra. Some of you have already learned it. And this tensor product comes with maps going in the opposite direction. Yeah, ring homomorphisms going in opposite direction. So Himanshu, can you tell me where you will send small a?
Yeah, A will go to A tensor with the identity of the other.
A tensored with the one in B.
Yeah, one in B.
And
Yeah.
B will go to one tensored with B. So to show this the identity in B, I write here and write here A. Okay, these are the ones. And so this is product, coproduct, and this much dose of category theory is enough for a long time now. And later on, we may need something more. Yeah? And I leave it to you, for you, Himanshu, and others who have understood this by now, that how will you define products and coproducts or arbitrary families of commutative rings? Okay, I leave that, figuring that out to you. Okay, so this is exactly 16:30, and I am going to stop lecturing, but I am not going to go away. And so I'm going to change the color and call it question answers. And now I'm at your disposal before the other speaker has to begin in 15 minutes from now. Here's your time in case you want to ask any clarification or any question. All mathematical questions are allowed. You don't have to stick to the syllabus.